Welcome back. At the end of the last video, I left you with a bit of a question. We had a situation where we had a 1 kilogram object. See, this is the 1 kilogram object, which I have drawn neater in this video. This is 1 kilogram. And we're on Earth, and it is, and I need to mention that because gravity is different from planet to planet. But as I mentioned, I'm holding it, let's say I'm holding it 10 meters above the ground. So this distance, or this height, is 10 meters. 10 meters, and we're assuming the acceleration of gravity, acceleration of gravity, which we also write as just g, is, let's assume it's just 10 meters per second squared, just for the simplicity of the math instead of the 9.8. So what we learned in the last video is that the potential energy in this situation, the potential energy, which equals m times g times h, is equal to, the mass is 1 kilogram times the acceleration of gravity, which is 10 meters per second squared. I'm not going to write the units now just to save space, although you should do this when you do it on your test. And then the height is 10 meters. And the units, if you work them all out, it's Newton meters or joules, and this equals, so it's equal to 100 joules. That's the potential energy when I'm holding it up there. And I asked you, well, when I let go, what happens? Well, the block obviously will start falling, and not only falling, it will start accelerating to the ground at 10 meters per second squared, roughly. And right before it hits the ground, let me draw that in brown for ground. Right before the object hits the ground, or actually right when it hits the ground, what will be the potential energy of the object? Well, it has no height, right? Potential energy is mgh. The mass and the acceleration of gravity stay the same, but the height is 0, so they're all multiplied by each other. So down here, the potential energy is going to be equal to 0. And I told you in the last video that we have the law of conservation of energy, that energy is conserved. It cannot be created or destroyed. It can just be converted from one form to another. But I'm just showing you, this object had 100 joules of energy, or in this case, gravitational potential energy. And down here, it has no energy. Or at least it has no gravitational potential energy, and that's the key. That gravitational potential energy was converted into something else. And that something else that was converted into is kinetic energy. And in this case, since it has no potential energy, all of that previous potential energy, all of this 100 joules that it has up here, all of this 100 joules is now going to be converted into kinetic energy. And we can use that information to figure out its velocity right before it hits the ground. So how do we do that? Well, what's the formula for kinetic energy? And we solved it 2 videos ago, and hopefully it shouldn't be too much of a mystery to you. It's something good to memorize, but it's also good to know how we got it, and go back 2 videos if you forgot. So kinetic energy, so first we know that all the potential energy was converted into kinetic energy. We had 100 joules of potential energy, so we're still going to have 100 joules, but now all of it's going to be kinetic energy. And kinetic energy is 1/2 mv squared. So we know that 1/2 mv squared, or the kinetic energy, is now going to equal 100 joules. What's the mass? The mass is 1. And we can solve for v now. 1/2 v squared is equal 100 joules. V squared is equal to 200. And then we get v is equal to square root of 200, which is something over 14. We can get the exact number. See, 200 square root 14.1 roughly. Velocity is going to be 14.1 meters per second squared downwards, right before the object touches the ground, right before it touches the ground. And you might say, well, Sal, that's nice and everything. That's, we learn a little bit about energy, but what, I could have solved that, or hopefully you could have solved that problem just using your kinematics formula. So what's the whole point of introducing these concepts of energy? And I will now show you. So let's say they have the same 1 kilogram object up here, and it's 10 meters in the air, but I'm going to change things a little bit. So let me see if I can competently erase all of this. Nope, that's not what I wanted to do. Okay, there you go. Trying my best to erase this. All of this stuff. Okay. So I have the same object. It's still 10 meters in the air, and I'll write that in a second. And I'm just holding there, and I'm still going to drop it, but something interesting is going to happen. Instead of it going straight down, it's actually going to drop on this ramp of ice. So the ice has lumps on it, and it's kind of and then this is the bottom. This is the ground down here. This is the ground. So what's going to happen this time? I'm still 10 meters in the air, so let me draw that. That's still 10 meters. I should switch colors just so not everything is ice. So that's still 10 meters, but instead of the object going straight down now, it's going to go down here and then start sliding, right? It's going to go sliding along this hill, and then at this point it's going to be going really fast in the horizontal direction, and right now we don't know how fast. And just using our kinematics formula, this would have been a really tough formula. This would have been difficult. I mean, you would have had to, you could have attempted, and it would actually have taken calculus because the angle of the slope changes continuously. We don't even know the formula for the angle of the slope. You would have had to break it out into vectors. You'd have to do all sorts of complicated things. This would have been a nearly impossible problem. But using energy, we can actually figure out what the velocity of this object is at this point. And we use the same idea. Here we have 100 joules of potential energy. We just figured that out. Down here, what's the height above the ground? Well, the height is 0. So all the potential energy has disappeared. And just like in the previous situation, all of the potential energy is now converted into kinetic energy. And so what is that kinetic energy going to equal? It's going to be equal to the initial potential energy. So here the kinetic energy is equal to 100 joules. 100 joules. And that equals 1/2 mv squared, just like we just solved. And if you solve for v, the mass is 1 kilogram. So the velocity in the horizontal direction will be, if you solve for it, 14.1 meters per second. Instead of going straight down, now it's going to be going in the horizontal to the right. And the reason why I said it was ice is because I wanted this to be frictionless, and I didn't want any energy lost to heat or anything like that. And you might say, okay, Sal, that's kind of interesting, and you kind of got the same number for the velocity than if I just dropped the object straight down, and that's interesting. But what else can this do for me? And this is where it's really cool. Not only can I figure out the velocity when all of the potential energies disappeared, but I can figure out the velocity at any point, and this is fascinating, along this slide. So let's say when the box is sliding down here. So let's say the box is at this point. It's it changes colors too as it falls. So this is the 1 kilogram box, right? It falls and it slides down here. And let's say at this point, its height above the ground is 5 meters. So what's its potential energy here? So let's just write something. All of the energy is conserved, right? So the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy, right? I'm just saying energy is conserved here. Up here, what's the initial total energy in the system? Well, the potential energy is 100, and the kinetic energy is 0 because it's stationary. I haven't dropped it yet. I haven't let go of it yet. So it's just stationary. So the initial energy is going to be equal to 100 joules. That's because this is 0 and this is 100. So the initial energy is 100 joules. At this point, what right here? What's the potential energy? Well, we're 5 meters up. So mass times gravity times height. Mass is 1 times gravity, 10 meters per second squared, times height times 5. So it's 50 joules. That's our potential energy at this point. And then we must have some kinetic energy going roughly, with the velocity going roughly in that direction, plus our kinetic energy at this point. And we know that no energy was destroyed. It's just converted. So we know the total energy still has to be 100 joules. So essentially what happened, and if we solve for this, it's very easy. Subtract 50 from both sides. We know that the kinetic energy is now also going to be equal to 50 joules. So what happened? Halfway down, essentially, half of the potential energy got converted to kinetic energy. And we can use this information, that the kinetic energy is 50 joules, to figure out the velocity at this point. 1/2 mv squared is equal to 50. The mass is 1. Multiply both sides by 2. You get v squared is equal to 100. The velocity is 10 meters per second along this crazy icy slide. And that is something that I would have challenged you to solve using traditional kinematics formulas, especially considering that we don't know really much about the surface of this slide. And even if we did, that would have been a million times harder than just using the law of conservation of energy and realizing that at this point half the potential energy is now kinetic energy. and it's going along the direction of the slide. I will see you in the next video.